So here I'm going to talk about our algorithm in the semi-streaming model for approximating maximum matching. So what is semi-streaming? Well, it's one of these modern models of processing big data, and the basic idea is just that you have some input data that is way too large to store on a single computer. So the memory of this machine is not enough to store the whole input data. In the semi-streaming, we have usually graphs that are represented with n nodes and m edges. And the idea is that the algorithm has much less space than the number of edges. And this is like in direct contrast with the centralized computing where you have your whole input stored on your tape. And for the sake of this talk, we have the memory fixed to roughly the number of nodes, but it could also be something different in principle. So, since we cannot store the whole graph in our memory, we have to get it in some other way. And in the streaming model, the edges are represented as a stream. So in every time step, one edge is presented to the algorithm, and then the algorithm can decide whether it should add it into its local memory or not. And here we don't really care about the local computation, so whatever information the machine has currently in its memory, you can compute whatever you like with it. Just one word about the representation of the graph. So each edge can be represented with the IDs of its endpoints. And here the identifier of the edge takes roughly log n bits, and we think of this as one word. And why is this important? Well, just because now the memory that is linear in the number of nodes actually means n log n bits. And in the semi-streaming model, we often assume that you can go over the stream of edges many times. So in one pass, you get to see each edge once. And we are allowed to do several ones of these passes, but we would like to minimize the number of them. So ideally, not many passes. I guess most of you are familiar with the maximum matching problem, but just to go over it quickly, in a matching we have a set of edges that don't intersect, and in the maximum cardinality matching the goal is to find the largest possible matching. We know that finding the optimum is kind of hard, so our goal is to aim for an approximation that is as close as possible to the optimum. And as the first thing, I would like to give a feeling of what kind of algorithms you can design in this streaming model. And our goal is to get a maximal matching, which just means a matching where you cannot add any more edges. So first we mark all the nodes as free. And in the first iteration, like when we obtain the first edge, we check whether the endpoints are free or not. And if they are free, then we can safely add this edge to the matching. And now we mark the endpoints as matched or non-free, and the goal is that now we know which nodes we are not allowed to use anymore for the matching. Alright, in the second step we get the edge E2. This guy is not adjacent to the matched edge, so we can again safely add this guy to the matching and mark the endpoints as non-free. If we get some edge that is connected to a matched endpoint, then we just throw this guy away, so we ignore that. And then we continue until we have gone through all the edges once and we have obtained a maximal matching. And you can see that just by considering any edge that could be added well, when we considered that edge, we would have added to the matching, so this thing has to be maximum. Clearly, we just need to go over the stream of edges once. And now, one important thing to notice is that we need to be able to, like for every one of these matched nodes, we need to know whether they are matched or not. And okay, here it's pretty easy to see that the matching can be of size at most n, because for every node we can have at most one matched edge. So we can clearly keep a matching in memory. So here, for example, our output matching is this maximal thing here, and we can keep this in memory. And well, for this algorithm, we actually don't need to keep anything else in memory. We know that one of these maximal, we know that the maximal matching is a 1.5 approximation to the maximum matching. So here you saw that kind of with a trivial algorithm, we can obtain a 1.5 approximation. And this kind of gives rise to this obvious question of, could we do something better? This problem has been studied for almost 20 years now, and the earliest result showed that you can get to something considerably better, like 2/3 approximation in, or let's say almost 2/3 approximation in a number of passes that is exponential in this epsilon. And the first algorithm was randomized. Then a tiny bit later, it was shown that you can actually make this approximation arbitrarily good, and you keep the same number of passes. And here maybe one good thing to point out is that it's not about the analysis in the sense that this algorithm can also take exponential in 1/epsilon passes to finish its computations. Then a bit later, these randomized algorithms were, well, let's say that the first randomized algorithm was matched with a deterministic algorithm, and in particular, the number of passes became polynomial. Then, a tiny bit later, we obtained a arbitrarily good approximation in polynomial number of passes, but here the last caveat is that this algorithm is for bipartite graphs. Then, some time later, a deterministic algorithm for arbitrary graphs was found, but here again the number of passes was exponential. And in our work, we show that you can do kind of best of all the worlds. So we have a polynomial amount of passes, we have a deterministic algorithm, and our approximation is as close to 1 as we want. And then a few words about lower bounds. So it is known that in a single pass you need a bit more than linear amount of space. On the other hand, it's known that if you go to linear amount of space, then you will need at least 1/epsilon passes, and it's like the question we were answering is somewhere in the middle ground, asking like how many passes do you need if you have tightly linear space. And this question is like not directly comparable with the lower bound results, but of course it would also be nice to get to know whether our algorithm is optimal, at least up to polynomial terms. And a bit more concretely, what we showed was that we get a semi-streaming algorithm with 1-epsilon approximation, and we need polynomial number of passes, and we need a tight memory in the sense that the output requires this many words to store. And the outline for the algorithm is of the following type. So we start with some some constant approximation, and for example here you can get this 2 or 1.5 approximate, 1/2 approximate matching by running this trivial maximal matching algorithm. And then for some polynomial amount of phases, we try to improve the matching by some 1+1/poly factor. And if you now kind of look at the numbers I inserted here, if we can do this improvement and we repeat it for poly 1/epsilon times, then we can make the approximation factor small. So basically our task is to implement the line in red. And the basic idea is that we would like to find a maximal set of augmenting paths of length at most 1/epsilon. This is kind of well-known approach from folklore, so if we could achieve this, then we would already be done. Unfortunately, it seems like achieving exactly this is a bit difficult. So instead of that, we actually want to just find some set that is almost maximal, and almost maximal in the sense that there's only poly 1/epsilon factor difference in a size of a maximal set and what we find. And this idea is not per se new. It was used in previous work. However, in the previous work, it only worked for bipartite graphs. And again, inspired by previous work, the goal is to run a parallel DFS search from all of the free nodes. And the free node is one of these guys who's not yet matched. And then, if we find an augmentation, then we remove the augmenting path from the graph, which corresponds to kind of fixing this into the maximal set, and we don't want to find any other paths that intersect with this found augmentation. However, one crucial difference is in this removing phrase that I wrote here, that instead of just removing an augmenting path, we also actually remove the whole DFS search from the graph, and we show that this doesn't hurt the process too much. So in a sense, instead of this like maximal set of augmenting paths, we are trying to find a maximal set of DFS searches. So now if we look at the algorithm that I displayed earlier, it becomes something like this, that we have this improving step, and this is divided into two, and first we do this parallel DFS search, and then we remove these DFS searches from the graph. And I'm not going to talk about this step number 2 here, but I'm just going to give a glimpse of how to do these parallel DFS searches. So the goal is to find these augmentations. So just imagine an augmenting path from alpha to beta, and our DFS search should find that. And this is actually the hard part of the algorithm, so there's a lot of details, but if you end up believing this, then the other steps are somewhat easier. The basic idea is that we start from a free vortex, then we go over the stream of edges, and eventually we see an edge incident on alpha. And now this alpha guy keeps this edge in memory, goes over another stream, and then it will find a matched edge. And now here it's good to notice that if there was no such matched edge, then we already could augment alpha with its neighbor. Now when you found this matched neighbor, then you label this matched edge with distance 1. So now here we know that from alpha to alpha 1 we have a distance of 1. Then we repeat this for A2, and do it inductively until a k minus 1. And ideally, we could now use induction to show that if we got to k minus 1, then we would also get to a of k, and then we could from that find beta. Unfortunately, it's not this simple, and this is kind of where the technical difficulties start. So now, if we, when we have these odd cycles in the graph, one of the things that can happen is that we start this search from alpha, and then we continue it, and we get into this sort of loop that we visited ai plus 1 already, and then we get back to ai, and we cannot continue this path anymore. So at least we don't have this nice inductive step that if I got to ai, I could also get to ai plus 1. And it can actually get even worse in the sense that there might be a DFS search from some other node, let's say beta, that we could continue to this edge ai plus 1. However, the search from beta is much longer in the sense that, let's say, it takes 100 steps to get to this edge that I displayed here. And the search of alpha was much shorter, and you could get to the next edge through a DFS search of 8 hops. And in a sense, it feels from the perspective of beta that now it doesn't make sense to continue the DFS search, because there is already a better DFS search going through this edge. What we showed is that this is not an issue, or actually this is a good case in the sense that now we already have an augmenting path from the node beta to node alpha. So putting it informally, we have that if alpha made this type of loop, we have an odd cycle, and then we can augment from alpha to beta. And there's one more thing that we observed, which is that it could also be that from alpha there's a longer path to this edge labeled with 8. So in a sense, alpha is blocking its own DFS search by the old DFS search that it did, because the first one was shorter. And now to put these observations into a tiny bit more formal box, is that what we showed is that if we ever found a path from alpha to ai, and we cannot continue to ai plus 1, then we have found an odd cycle. So in a sense, this is similar to the classic Blossom algorithm, where we can think of this odd cycle here as good in the sense that no other node can have a search here without finding an augmenting path. And now, essentially, we can think of this AX and AI being good in the sense that this will always stay in the DFS search tree of alpha, and no one can mess with them. What we showed is that this will be true for all the edges between this loop that the alpha did and the edge where it wants to go. And what we can now show is that alpha will kind of keep this path from AX to AI in memory, then the DFS search will eventually backtrack to the edge I displayed on the left, and then we have all the necessary information we need to now kind of extend this short DFS search over this blue box to the right. And then we kind of have the means to do this type of inductive argument that I wanted to do before, which is that if alpha finds a path of length, a path from itself to AI, then a lot of things can happen, but eventually we have this short DFS path that we will then extend to AI plus 1. So either we augment already earlier, or alpha will eventually find this path. And now we are done with the high-level overview of what we would like to do. And then just a quick recap of our approach. So we do this truncated DFS search from each node. By that we find an almost maximal set of augmenting paths, and we can use this by previous work to improve the matching by this poly 1 over epsilon factor, while we then can repeat this poly 1 over epsilon times, and we obtain an almost optimal maximum cardinality. We obtain an approximation to the maximum cardinality matching that we can make arbitrarily good. And then I just display this theorem here again and show a nice picture of a graph